In this video, I plan to talk about the concept of magnetic flux. The magnetic flux is shown by symbol phi, or sometimes referred to as phi. And it is defined for an area. For example, this is the area that we are talking about in this slide, and so it's defined for an area. It's defined as this is because this is the magnetic flux. It's defined in terms of the magnetic field where this area is present, the value of that area. So this is area. So you will literally calculate this area, you put that value there, and this is the magnetic field. This is the magnetic field. And theta is defined as the angle between the magnetic field vector, which is shown by this arrow pointing downward, and another quantity, another direction called normal to the area. Normal to the area refers to a perpendicular direction. So in our picture, the normal would be, if this is your area like a plane, the normal would be pointing up. So let me draw this up. It should be a straight line. This is your normal. And theta is defined as the angle between the normal and the B vector. And you use that formula, and that gives you the flux. And the unit of flux will come out to be this, the SI unit. And the interesting point is that any change in the magnetic flux will produce an EMF in this coil. If this green color coil that we're talking about, so assume that this is just a periphery and that's a coil. This is not a sheet of metal, but instead it's a coil. In this coil, the EMF will get induced, and which will result in the current flowing in this coil. That is all happening because the flux changes with time, and it is called Faraday's principle of induction. Now let's calculate the flux of a coil using the formula that we had seen in the previous slide. So in this problem, it says, in your classroom, the Earth's magnetic flux is given to be 55 microtesla. So because this is Earth's magnetic, this should be magnetic field, not flux. I apologize for the mistake. And so the symbol for denoting magnetic field is B. Because by looking at the units, we can say it cannot be flux, it has to be magnetic field value. And the magnetic field makes an angle of 60 degrees below the horizontal surface of your study table. So essentially this is your study table, and the problem is set up in such a way that the magnetic field points at 60 degrees below your table, just like it's shown in the picture. And the dimensions, so this is theta, which happens to be the angle between the normal to your table, which will be literally going upward. That's your normal. And the magnetic field, which was shown by the magenta arrows pointing downward. So this is your theta. This is your normal. Normal is perpendicular to your table. And the dimensions of the table are given. This is useful in getting the area of the table. And the question is asking, what is the magnetic flux through the surface of a table? Now we must know that this table is not a conductor, it's a wooden material, and we will get a flux by using the formula, and the formula is this that was presented. We have all these quantities: magnetic field, the area, and the cos theta, and that gives you this field. Now, important point to remember is that this problem just asks us to calculate magnetic flux, and even if this flux were to be changing, because it's a wooden table, we will not have induced EMF across this table. Okay, this is the problem is just for calculation of flux.